So you can pause to read the problem yourself. So the theory is that we know that velocity is defined to be the distance over time. So for instantaneous velocity, it's the small distance of x over the small distance of t, and we can uh, move this to the left side, so we can v dt equals to dx. So we can integrate both sides, and integral v dt becomes integral v dt, and integral dx is x itself. So we are asked to find distance traveled from here to here. So from this equation, we just have to find the area of this graph. So we can divide the area by three parts. That is the first triangle here, and second the triangle here, and the third is the rectangle here. So to find the area of the triangle, we know that area of triangle is a half times base times height, and the base is t1. So the base of 1 is t1, and the height of area 1 is v1. So we can write a half times v1 times t1. And for area 2, the base is the distance from t1 to t2, and the height is the distance from v1 to v2. And we know that from O to t2 is t2, and from O to t1 is t1. So to find the distance from t1 to t2, we can just subtract here to here at t2 minus t1. So the base of area 2 is t2 minus t1, and for the height is the same. v2 minus v1 is the height of area 2. So we can write the area of area 2 is a half times the base, that is t2 minus t1, times the height v2 minus v1, and the area 3 is just a rectangle. So the base is t2 minus t1 times the height, that is from O to v1, that is v1. So we can write t2 minus t1 times v1. So to find the distance is just the sum of all of these areas. So we sum all of these, and we can brute force this. We can multiply all of this and all of these, and it became like this. And we find if we can subtract or add something, see if there is the same variables. So we search for v1 and t1. So this is not v1 t1, this is not v1 t1, this is not v1 t1, this is v1 t1, this is not v1 t1, this is v1 t1. So we add all of them. So a half plus a half is 1, minus 1 is 0. So we can cancel v1 t1. So a half plus a half minus 1 is just 0, so we can cancel them. So for v2 t2, there's no other variable, there is v2 t2. So we can write them as is. And for v2 t1, there's no other variable, that is v2 t1. So we can write it as is. So for v1 and t2, there is other v1 t2, there is 1. So minus a half plus 1 is a half. So we can write a half times v1 times t2, and we can write this as this. That is the answer B. So you can pause again to read the problem. So we are asked to find the heat required for this process. So the theory is that when there's something, say a block, to find the heat that is into the block is equal to the change of the internal energy of the block plus the work that is out to the environment by the block. And we can write the change of the internal energy as 3 over 2 times nr times the change of the temperature, and the work that is out to the environment is P times the change of the volume. And we have to know that PV is equal to nRT. So we substitute this to here and this to here, so we get this. And the change of the temperature is just the temperature after. We can, let's say it's T2 minus the temperature before, let's say T1. So and change of the volume is just the change is just the after the volume after minus the volume before, that is from the problem is V2 minus the volume before from the problem it's V1. And from the fact that PV is equal to nRT, we know that P is constant, so P is V itself times V1. So we know that P times the V before is equal to nR times T, that is before the process. So we can write nRT1 as VV1, and the same goes for the volume after the process. So the volume after, so P times V after the process is equal to nRT after the process. So we can write nRT2 to PV2. So we can write it like this, and we can just add both of these, that is 5 over 2, that is the answer D. So you can read the problem yourself. And the keyword is that the direction of the research is taken as the positive direction. So first we have to know the theory is that whenever there is a wave like this, we can write the height, we can express the y coordinate as a times sine times the angular frequency times t. So whenever there is a wave with the height of a, we can write it like this. And this doesn't have to be sine, it can be cosine minus sine or whatever. So this depends on the shape of the wave. So to illustrate the problem, so let there be a wall with a block stretched from its natural position, that is here, to the distance d, and we take the direction of the stretch as a positive direction. So what happens when it's released is that it'll move to this direction, it'll move to the wall, then it will come back to here and will repeat to the wall and come back to here. So it will repeat, and we can illustrate like this. And we can express the position the of the block. So we take the right direction as the positive direction and the left direction as the minus direction, and we treat this wave as time goes on, it will uh, shape a wave like this. So we can express it as a graph. So from a height of d, it moves like this. So this is the position x. So it is the graph expressing x as it goes over time. So we notice that it has the height of d, or the amplitude of d, so we can write d times the wave function, and we know that this is cosine, so we can write cosine angular frequency times t from the theory here. So we are asked the velocity of the block, and to find the velocity, we know that we can derive velocity in respect to time. We can derive xt in respect to time. So we can just derive this, and derivative of cosine is minus sine, and we can use the chain rule to get out omega to the outside, so it became minus omega d sine omega t. So it has the amplitude of omega d, and it matches the answers, and the function is minus sine, so so the answer that has minus sign is B, so the answer is B. So the theory is that when there are two charges, just when they are both positive, they repel each other. When the charge is different, they attract each other. And to express the force of each of those charge, we can express it as 1 over 4 pi epsilon naught times q of this times q of this over the distance squared. And we know that the force of spring is k times d. So let me illustrate like this. So at first there is a small q here, and then there's a big Q appears at distance L, and because they're both positive, they repel each other, so Q will move repelling big Q. But there is a spring here, so the spring pushes back to the right direction. So the forces that is acting on small q is the force that is exerted by big Q minus the force by the spring. And from B, we know that it is stable at distance d. So what does it mean for it to be stable? So it stops moving. So it doesn't go anywhere, so it's stable at D. It doesn't move at all at distance D. What it means to be stable is that the force that is acting on the left, that is forced by big Q, is equal to this force that is acted by the spring. So we can write the force by the spring is equal to the force by the big Q. So we can write KD is equal to 1 over 4 pi epsilon naught times big Q times Q over the distance. The distance here is L. From L to 0 is L, and from 0 to D is D, so it is L plus D squared. And to find big Q, we can move this to the top of here, and Q to the bottom. So it became like this, and it is the answer A. So we are asked to find the refractive index N. So the theory is that the refractive index, that is N of here, times sine of the theta that is adjacent to the normal line, that is the vertical line, is equal to N2 here times sine of theta that is adjacent to the line here, adjacent to the normal line here. And we have to know that the refractive index of air is 1. So from this problem we know that uh, from here we have to express it as this equation. So you can write an air times sine of this angle. So why don't we use theta is because this is not adjacent to the normal line. So we make an angle that is adjacent to the normal line, so let's call it alpha. N is equal to the refractive index of N here times sine beta. So it became this equation. And to find sine alpha, we know that sine is equal to the opposite over the hypotenuse. So the opposite of alpha, so here is the same angle as here. So we can know the sine of the alpha is d over the hypotenuse here, and same goes for beta. So we can write this as a triangle like this. And from Pythagorean theorem we know that h squared plus b squared is equal to c squared. So we know that the hypotenuse is h squared plus d squared with square root, and same goes for beta. So back to the sine alpha equals to n sine beta. We know that sine theta is opposite over hypotenuse, so the opposite of alpha is d, and the hypotenuse of alpha is h squared plus d squared, so it is like this. And for sine beta, it is the opposite. So its opposite is d minus x over this. So we can write it like this. And to find the refractive index n, we just have to move x squared plus d minus x squared to the top here and d minus x to the bottom here. So it became the answer D.